Yes, dear friends, today we are discussing an important topic of series LCR circuit, the Q factors. Q factors of a series LCR circuit is the relationship between current amplitude and the frequency of the LCR circuit. We know that if I draw the graph between current amplitude and the different values of angular frequency of the AC voltage applied, we have seen that this is the graph of this one. So here, I have taken the graph between I naught and omega for three different values of resistance in the LCR circuit. One is for the low value of R, second one is for medium R, and third one's for high value of R. Third graph is for high value of R. So look at the graph. So when I goes from the lower graph to the higher graph, the sharpness, the peak of the graph, the flatness of the graph is decreasing. It is more flat, this is less flat, and this is least flat. It means that sharpness of the graph is increasing when the resistance of the LCR circuit, that is the R, is decreasing. So exactly, but the amplitude of the current at a particular frequency, that is known as the resonant frequency, all have the same one. So you know that at omega, this is the value of resonance frequency at which in the LCR circuit the current become maximum. So resonance frequency of all the three resistors are the same. It means that this will not change for if you change the resistance in the LCR circuits. So all have the peak getting at the same point, that is known as the resonant frequency. So quality factors generally defined a relationship between the current amplitude and a particular value of frequency of LCR circuits. So at a particular value of angular frequency of the AC circuits, the current amplitude become maximum. So more the quality factors. If a LCR circuit has more quality factors, then it would be more sharpness in the current amplitude and omega. Now mathematically, how to calculate the Q factors of series LCR circuit. We know that this is the graph between current in LCR circuit and the corresponding frequency of the AC voltage applied. To look at the graphs, so when the frequency is increasing, from here to a frequency increasing, correspondingly current is also increased in the circuits. After this a particular frequency known as the resonant frequency, our current goes on decreasing when the frequency goes on increasing. So this graph is symmetrical about this vertical line which is passing through the resonant frequency. You know that at the resonant frequency the current amplitude in the series LCR circuit becomes maximum. So this is the maximum value at this frequency, which is omega r, known as resonant frequency. So both the side of the resonant frequency at a particular distance, this one. So this is the height of this one. So both frequency, if I say that this will be omega 1 and this is omega 2. So at omega 1, omega 2 frequency, at these two frequency, current amplitude have the same value. So if I say that if the current amplitude, if this is maximum amplitude at this one, if this is the maximum amplitude at the resonant frequency, if the frequency at this point is just maximum amplitude divided by root 2, at maximum amplitude of the current divided by root 2, corresponding frequency in the frequency axis would be omega 1, omega 2. So our definition of the Q factor of the LCR circuit is resonant frequency divided by corresponding frequency to the current amplitude divided by root 2. Maximum current amplitude divided by root 2, it means that omega 2 minus omega 1. This is also known as the bandwidth. So here omega 2 minus omega r. If I say that this is the difference of these two frequency, delta omega. Similarly, omega r maximum value and omega 1 is lesser value of that. Difference between them is omega r minus omega 1 is equal to delta omega. So if I place the value here, omega 2 minus omega 1, this is delta omega, this is also delta omega. So distance between them becomes two times of the delta omega. This delta omega known as the bandwidth. This is the bandwidth of the LCR circuit. So the definition of the Q factor of the LCR circuit is resonant frequency divided by twice of the bandwidth. So lesser the bandwidth, lesser the value of the bandwidth, more will be the quality factor, more will be the sharpness of the current and frequency graph. Sharpness means this is the sharpness. It means that it has a peak, a sharp peak of this graph will known as the sharpness. This sharpness of the LCR circuit defined by this formula. So omega 1 omega 2 are the corresponding value when the current amplitude becomes I naught upon root 2. So at the I naught upon root 2 corresponding frequency, which one is omega 1, another one is omega 2. So difference between them, omega 2 minus omega n, will be equal twice of the bandwidth. So it will define. So mathematically this is the expression for the Q factors of series LCR circuit. So this is a bandwidth graph of series LCR circuit. And corresponding mathematical formula will be this one. So now how to calculate the expression for this quality factors, also known as Q factors of this LCR circuit in other way. Let us start. Now let us start expression for Q factor. Q factor of LCR circuit. Now first of all, we know that impedance we generally represent by Z. Impedance at resonant frequency will be just ohmic resistance. But what would be the impedance at the frequency of omega 1 omega 2? So corresponding to omega 1, the current amplitude I naught upon root 2, and same way corresponding to the omega 2, current amplitude is I naught upon root 2. So for finding the impedance at omega 1 omega 2, we can say Z is equal to voltage divided by current amplitude at this one will be I naught divided by root 2. This is why the ohmic resistance, voltage divided by current will be the resistance. Impedance means the resistance of the series LCR circuit. So from here omega 2 into E naught divided by naught. We already know that when the resistance at the resonant frequency, we have the impedance Z is equal to R. It has the value E naught divided by I naught. So from here E naught upon I naught will be root 2 R. So our impedance at frequency omega 1 omega 2 will be root 2 times of R. Now from the formula of impedance, let us suppose we represent this impedance or resistance of the series LCR circuit is Z, square of the ohmic resistance plus resistance of inductor minus resistance of the capacitors whole square. If I place the value of XL and XC, it comes out r square plus omega L minus omega c of whole square. So we have to put the value of impedance at the corresponding omega and omega 2. We are to find the value of omega 2 minus omega 1. Omega 2 minus omega 1, which is 2 times of the bandwidth, because our aim is to find the quality factor. The quality factor is the ratio of the resonant frequency divided by omega 2 minus omega 1. It means that twice delta omega. So from here we will get the value of 2 times of del omega. So at the frequency of omega and omega 2, our impedance is Z is equal to root 2R. Now the formula of the impedance is equal to this one. If I put the value of Z, which is root 2R, and at the angular frequency omega and omega 2, it becomes root 2D into R, squaring both the sides. So now if I square both the sides, it will be R square plus omega L minus omega C whole square is equal to twice R square. Now from equation number first, if I calculate this one, R square now R square plus omega L minus omega C whole square is equal to twice R square. If I place this value to the right hand side, it comes out omega L minus 1 upon omega C whole square. It comes out 2R square minus R square. It becomes simply square of R. So square of this term is equal to R square. From here omega L minus omega C is equal to plus minus R. So it has two value. It has two value corresponding to omega 1 and omega 2. Now these two values, if I represent by omega L minus omega 1L minus 1 upon omega 1C is equal to suppose minus R, and another value I can place omega 2L minus 1 upon omega 2C is equal to plus R. Suppose this is equation number 1, and second equations corresponding to omega 2 the angular frequency at which your current amplitude is I naught upon 2. It means that maximum current amplitude divided by root 2. Now it becomes omega 2L minus 1 upon omega 2C is equal to plus R. This is equation number second. Now adding and subtractions. If I add both these equations and subtract these two equations, I have get first one, adding equation first and second, I will get the value, adding these two, omega 1L, add this value on this omega 2L and add this value with this, minus omega 1C minus omega 2C is equal to minus R plus R. It has the value minus R, it has the value plus R, minus R plus R becomes 0. Now taken L common from here, omega 1 plus omega 2 multiplied L minus, taking the LCM here, omega 1, omega 2, omega C is the LCM, omega 1, omega 2 C, and simply solving this one, minus omega 2 and minus omega 1 go this side is equal to 0. So now place this value in right hand side. Now from this expression, if I write here omega 1 plus omega 2 times L is equal to omega 1 omega 2 divided by omega 1 omega 2 and C. It can be cancelled. So finally I am able to find out the value L is equal to 1 upon omega 1 omega 2 times of C. If I take omega and omega 2 in the numerators, omega and omega 2 is equal to 1 upon CL. This is one value of omega and omega 2 after adding first and second. Now let's put this in equation number 3rd. Now from equation first and second, if I subtract first and second, now subtracting from equation number first the equation number second, I will be able to find this minus this. Now omega 1L minus omega 2L, second term is this omega 1C and minus omega 2C is equal to minus R. So we also do this part first minus second in this way also. First minus this taken as a whole, these terms minus as a whole these terms is equal to this minus this. So what it comes? So if I write this like omega 1L minus omega 1C minus this term omega 2L minus omega 2C, in the right hand side minus R and minus R, it becomes minus 2R, and from here taken this term with this term and this term with this terms. So what it comes? Omega 1L minus omega 2L, omega 1L minus omega 2L, and similarly corresponding to these terms I would take this term. So here this term is equal to minus 1 upon omega C, minus to minus become plus 1 upon omega 2C is equal to minus 2R. So this is the value. Yes. So now from here, if I take L outside and 1 by C taken outside, then taking the LCMs and using omega and omega 2 1 upon CL, I will be able to find out omega 2 minus omega 1. Now from this expression, from here, if I take L common, it comes out omega 1 minus omega 2, outside will be L, and taken 1 by C is common from here, plus 1 by C. Inside of this ones 1 upon omega 2, 1 upon omega 2 minus 1 upon omega 2 minus 1 by omega 1 is equal to minus 2R. Now take LCM here. This is omega 1 minus omega 2 L plus 1 by C. Take the LCM, which is omega 1 omega 2, omega 1 go this side, minus omega 2 is equal to minus 2R. Look at this value here, omega 1 omega 2 are common between them. If I take this outside, so it comes out omega 1 minus omega 2 inside of this will be L plus 1 by C times omega 1 omega 2. It means that omega 1 omega 2 times of C, bracket is closed, is equal to minus 2R. Now if I use equation number 3, omega 1 omega 2, which is equal to 1 by CL, place this value here. So I will get from here, yes, take this part, omega 1 minus omega 2, omega 1 minus omega 2 inside of this one, L plus, place the value of omega 1 omega 2, 1 by CL. So it comes out 1 upon CL times C, bracket is closed, is equal to minus 2R. If I cancel this, this L goes in the numerator. Finally, omega 1 omega 2 is equal to L plus L, bracket close, minus 2R. So it becomes twice L. From here, omega 1 minus omega 2 and into twice L is equal to minus 2R. If I remove 2 from here, so here omega L times omega 1 omega minus L times omega 1 minus omega 2 is equal to minus R. We know that omega 2 greater than omega 1, so taken minus from here, so I will be able to find minus L, omega 2 minus omega 1 is equal to minus R. Minus is cancelled out, this value becomes here L times omega 2 minus omega 1 is equal to R. From here I will be able to find omega 2 minus omega 1, which is the bandwidth, twice of the bandwidth of this series LCR circuit. Now over from the last expression, from our last expression, which is this one, from here omega 2 minus omega 1, omega 2 minus omega 1 is equal to R divided by L. This is the expressions for twice of the bandwidth, and we know that the quality factor of this, quality factors or Q factor of this series LCR circuit is equal to resonant frequency divided by twice of the bandwidth. It means that omega 2 minus omega 1, if I place the value of omega has the value 1 upon root CL divided by omega 2 minus omega 1 has the value R upon L. Just simplifications, I will be able to calculate this one, 1 upon root CL times L upon R. Just simplifications, L has the value root L into root L, 1 cancelled out. Now if I place L has the value root L into root L divided by R times of square root of CL. So root L 1 cancelled, and what remains is there only 1 upon R root L upon root L upon C. This is another expression for the Q factors, another expression of the Q factors. This is one of the formula of the quality factors. Another formulas I would like to go, and we know that the quality factors is equal to resonance frequency divided by omega 2 minus omega 1. You know that omega 2 minus omega 1 is equal to R upon L, R upon L. Now this value comes out omega R multiplied L divided by R. If I multiply the RMS value of the current, RMS value of the current is average current in AC circuits, omega R L multiplied RMS value of the current, IRMS divided by RMS value of the current multiplied R. So now we know that this is a inductive reactance in series LCR circuit. Just we write this like RMS current multiplied XL divided by RMS multiplied R. From here, this is the voltage drop across the inductor. Voltage drop drop across inductor, L means inductor, divided by IRMS into our applied voltage. This is known as the applied voltage. Applied voltage, because at applied voltage, when the applied voltage are at resonant frequency, your impedance of the LCR circuit becomes only ohmic resistance. So whatever the voltage across the ohmic resistance will be the applied voltage. So here the voltage drop across the inductor divided by applied voltage. We know that at the resonant frequency, voltage across inductor is more than that of the applied voltage. Here the voltage across the inductor is more than that of the applied voltage. So we can say that this is the voltage magnification. So here it become a voltage magnified. This appliances has magnified the voltage. So we call this voltage magnification. Voltage magnification. Now this value becomes the quality factors voltage drops across inductors divided by applied voltage, known as voltage magnification. Here the voltage across the inductors, we already know that at the resonant frequency, voltage across the inductor is always greater than the applied voltage. So we can also change by the formula of the ohmic resistance. We know at resonant frequency the value of omega has root LC. We can also convert this inductor's XL in terms of XC. So therefore voltage magnification has another value. Now your quality factor same way as in earlier case. Resonant frequency divided by omega 2 minus omega 1, it has the value R upon L. Resonant frequency divided by R divided by L, L goes in the numerator, and also using this value we are need remove the L from here. So if I place the value of L from here, it comes out omega R. If I write this root L whole square will be L divided by R. Its value coming from here 1 upon root L. This root L goes in this side and omega R goes this side. It becomes 1 upon omega R into root C. If I place these values here,